Let me introduce to you Chuck Rogers. He has a master's degree in physics. He worked with the Northwest Critical Mass Lab and is a nuclear safety specialist. And his presentation is the free electron model of image formation on the Shroud of Turin. Thank you.
Hello. This is a highly independent theoretical report on how God would create an image on a cloth. My hypothesis is this. The man in the cloth was vanished. He was pulled into a higher dimensionality and simply disappeared. Now, that is something that we have never seen scientifically, but modern physics does say there are higher universes, ultimate universes in higher dimensions. And so it's theoretically possible. In fact, we may already live in a universe that has higher dimensions. The reason we don't get this transfer very often is there's a potential energy barrier that prevents it. So energy and matter cannot transfer willy-nilly. In fact, it almost never does. And so we have a situation here which you would expect to use quantum tunneling to solve, but we have an entire man that disappeared. That is not something that requires quantum mechanics because the barrier had to completely break down. So you can use classical electrodynamics. So now it's simple. Anyway, there had to be only a small release of energy on our side of the boundary. There could have been a big release of energy on the other side. May have produced neutrons. Okay, what I've done is create what I call the free electron model of image creation. I have a series of steps, that's how I define it. The thing that you have to have that's essential are free electrons. Well, the center of the body, the core, has liquid, produces positive, negative ions. Electrons go back and forth between those ions. And when they're in between, they're free. And those are the ones that can create the image. The next thing you need is an interface. The interface has to open up between our world and these higher dimensions or this other universe, whatever it might be. And because the image is uniform on the top and the bottom, and looking at how this image was formed, this interface had to open up on the midplane of the body. It extended out the arms, it extended out the legs, it extended sideways to the edges of the body. When body material passed through that interface, it just simply disappeared. Free electrons, however, they're moving in every direction. So some of them will remain in that cavity. And the ones that remain will create a charged layer on the two interface boundaries where there's still material. The boundaries are moving up and down. These charged layers form in front of those boundaries and they move along with them. So we got charged layers moving up and down. The vertical sides will not produce an image because the interface extends all the way to the side, takes in all the material off of the side. There's nothing left there to make an image. There are no image on vertical sides, except two exceptions I'll mention later. Anyway, did I skip one? Yes. Seems like I must have. Got to hurry here. The skin encloses all the material that disappears. Electrons in the cavity form these charge layers. They move in front of the interface surfaces. When they reach the surface, they cast an electronic shadow. So now you have an electronic shadow on the linen. The linen has a very low conductivity, so the electrons just sit there and wait for something to happen. If electrons go through the air gaps, they get attenuated. So you get areas on the cloth which have no charge. Now you get a charge-induced chemical reaction where the electronic shadow is, and you get air gaps. These combine to create a complete image of a man on the top and bottom surfaces. At the beginning, it's invisible. Then it turns straw yellow over time, and that's the end of the process. We're done, at least with the image, not the explanation. Anyway, here is a picture showing how the body is arranged and how the cloth is arranged. The body is put on a slab, or the cloth is put on the slab first, the body is put on the cloth is folded over the head and comes all the way down to here. It does not go over the feet. Then there are 3 pieces of cloth used to tie the body. These are actually tied on there fairly tight. And a 4th piece of cloth that's called the jaw band that goes over the top of the head, under the chin, and it is special. It's underneath of the cloth of the shroud. So it can actually do things that the others can't. Okay, we need free electrons. We get free electrons in the middle of the body where there's solution. And that's enough to get the process started. However, as the interfaces move towards the outer surface, the number of free electrons decrease. There is not enough free electrons here to create an image unless we come up with some more. How we do that is that in the charge layers, the electrons are powerful enough to strip off additional electrons off of elements that have low ionization potential. This is calcium, sodium, and potassium primarily. So that has an ability to keep the charge layer going until it has to continue until it hits the surface. The conditions for this process are very precise. You can't screw up very much or you're not going to have an image. Somebody knew what they were doing when they did this. Anyway, this shows how the electrons move back and forth across a fully open cavity. When I say fully open, the only body material left at this point is right along the surface, top and bottom. Electrons are going back and forth. In the middle here, we have a center of charge. If an electron is away from that center of charge, it's pushed away. So electrons, as they go back and forth, will accelerate towards the feed. They'll go out the end of the feed. On the other side, they'll go out the top of the head. This creates a current flowing out of the feed and flowing out of the head. That has an important consequence on the image. Okay, I've mentioned certain things, so let's review them real quick. Oops, not that way. Buttons are close together. Right here is the image of the jaw band, I maintain, that dark band. So there is actually an image on the vertical surface here. The feet, where this charge is flowing out of, also has an image, but it's indistinct, caused by the flow of electricity. So these are the only 2 vertical surfaces that have images. No other surface. The top of the head is the brightest part, the bottom of the feed. Okay, then the image, when it's formed, if the cloth is in contact, like it is here on the chest, you get a bright image. If the cloth is away from the skin, you get a dark image. And you need the light and dark patches both to create the image. Okay, I think that's enough for that one. Oops. Is that really where I'm at? Okay, must be. I was thinking there was something else in between, but I assume this is correct. But anyway, what we have to do is find out what the energy of the free electrons is. To do that, you have to use the Fermi free electron gas model. With a little bit of quantum mechanics and statistical mechanics and some of that stuff, you'll come up with it. Wrong button again. I should probably stop using this button. Okay, there's this button. You come up with this formula for the probability distribution as a function of energy. And it's equal to 1 over 1 plus the e to this exponent. E, electron energy minus the Fermi energy, divided by the Boltzmann constant times the temperature. The Boltzmann constant times the temperature is actually a relatively small number. That leads to a relatively small value of E sub f, which is the Fermi energy. It turns out that the Fermi energy is 7 electron volts. From 0 up to 7 electron volts, you have a uniform distribution of electron energies. And then it just drops right off to 0. So you can say with great certainty that none of these electrons are going to have more than 7 electron volts. The problem with that is it won't create an image, not enough energy. So God had to come up with a solution here, which is the charge layers. He produced charge layers in here. When you have these electron volts of 7 energy inside of the cavity, they hit the charge layer on the inside. There's 7 electron volts. But as they move forward in the charge layer, the distribution of charge in front of them and in back of them shifts, and they're pushed forward with greater energy. They reach their maximum energy when they reach the front edge of the charge layer. Now what we need to do is figure out how much energy they have when they get to the front edge of the charge layer. We do that by looking at the image on the shroud and try to figure out how far the cloth has to be from the skin for there to be no image. Turns out that's about 2 centimeters. So the stopping distance of electrons is about 2 centimeters that are coming out of the front of the charge layer. If you look on the table, you find this corresponds to 25 electron volts. So now we've gone from 7 electron volts to 25 kilovolts, 25 kiloelectron volts. That's a factor of 3 to 4,000 increase. We now have enough energy to create an image. Okay, let's look at the angular distribution of electrons coming out of the skin. There's two distributions that are important: lateral, longitudinal. They're very different. Okay, got to get the right button. Right here, this is a cross-section of the torso at the point when the image forms. The maximum span of angles, I estimate to be 82 degrees. But it doesn't stay 82 degrees because the charge layer is decreasing in width very rapidly. So this goes to 0. So that the actual span of angles that creates the image is really quite small, probably less than 10 degrees. But in the longitudinal direction, it's very different. The image is disappearing sideways, so the lengthwise stays exactly constant. So there is no change in this lateral, or this span of angles. And this 126-degree estimate I have here is a minimum span. It actually goes all the way up to 180 degrees. So what you got, lateral direction, small span of angles; longitudinal direction, big span of angles. If you take a drop of blood on the surface of that skin, run this distribution of electrons through it, it stretches. So what you get is stretched images. This is called striation. And that image is highly striated, and striation actually tells you something about how it's been created. Now, the next thing that we need to know is how many electrons are we to find on the charge layers. I have put together this formula to determine that. First thing I'll mention is that T is the thickness of the charge layers, which is about 10 to the minus 5 meters. That's not as thick as a sheet of paper. And that's also the encoding layer. So anything that's further in from the top of the skin than a sheet of paper will not be encoded on the image. It's only that top surface, with some modification, which takes a while to explain, but just assume that that's true. So anyway, the total number of electrons in the charge layer is 2 times the total number of electrons in the body, times the thickness of the charge layer, divided by the thickness of the torso, which is 1/4 meter, times the fraction of electrons that are free, times the fraction of electrons that enter the cavity and successfully cross to the opposite side. The important thing about this formula is 2 of these factors are a function of x, which is the width of the cavity. So this is not a constant. And that turns out to have some significance. So now the question is, how much charge is there? So the simplest way to estimate that is to use a hollow metal sphere as a model. The charge on a hollow metal sphere, gotta hit the right button, is Q equals 4 pi times epsilon sub 0 times the radius of the sphere times the voltage. Epsilon sub 0 is a constant. It's the permittivity of free space. When the surface area of the sphere is 0.41 meters, the area of the sphere is the same as the area of the body. So now it makes a good model for the body. So if we plug this into this formula, we get this formula, which says that Q is 4.5 times 10 to the minus 11 times the voltage on the skin. So now we have a relationship between charge and voltage. What's really interesting, in my opinion, is how many electrons are involved. So we can get that fairly easy if we know the number of electrons in 1 coulomb. Then we multiply those two together, we come up with this value here. And this is the number of electrons on the hollow sphere. The voltage on the hollow sphere now is set equal to 25 kilovolts, which is a voltage that we determined was on the skin of the body. This means that the total number of electrons in this system is 7.1 times 10 to the 12th. That's the number of electrons required to create the image on the shroud. If we take the area surface density is an interesting number, at least theoretically, and that's when you divide by the area, and you come up with an average of 5 times 10 to the 8 electronic charges per square centimeter. That's the charge on the surface of the cloth on average. Okay, now let's do a thought experiment. We have some data. What can we do with it? Well, we have a formula for the charge on the two layers, and that formula has this factor and this factor, F sub F and F sub C. It turns out both of these are larger for a narrow cavity, and they decrease rather rapidly as the cavity opens. So F sub F, the number of free electrons, gets much smaller as the cavity opens because there's less liquid out there, less ions, less free electrons. The other one, this one gets smaller as it opens because the leakage increases, both into the other dimension and out the sides. So what I would estimate, just for the sake of argument, is that both of these are 10 times larger for a small cavity as for a large cavity. So we have this number. When we plug that into our formula, what we conclude is a narrow cavity can have 100 times more electric charge than a wide cavity. That's important, actually. And I'll show you why when we plot the curve. So the voltage before the cavity starts to open is 0. But as soon as it opens, the charge layers start build up. They build up very rapidly. F sub F and F sub C are dropping now. So you reach a maximum value right here, and then it dissipates until you get to the skin, which we decided had a voltage of 25,000 volts. I don't know what this maximum voltage is exactly, but it's at least 10 times this voltage. So the maximum voltage in on the charge while in the body, as these interfaces are opening up, is at least 250,000 volts. My personal opinion is it's a lot bigger than that. I think it's over 1 million volts. That would shoot it way off the top, and then it would come back real fast. It's like a burst of lightning, actually. That's a good analogy. But that's something to figure out later. Okay, let's go to the next one. Now let's look at the image itself. I guess my time is still going. 1 millionth of a second before the legs disappear. This is a cross-section of the legs. All that's left, oops, wrong button again. You'd think I'd learn. Okay, here we are. This is all the flesh that's left in this leg, top and bottom. This is all void in the middle. The legs will be gone in another millionth of a second. But if we look at the image, we find that this area right here, which is the shroud in between, is dark. Dark means no electrons. There ought to be electrons there, but there isn't. And the reason is there's air here. The air didn't disappear. The air stayed. So the interface between our world and this higher dimensionality ends at the skin. And so here, it stops at the skin, it leaves the air intact. That's an important factor on understanding the overall image. It gets pretty highly complicated, however. But we also have photons. A lot of photons are generated. That's where this coronal discharge stuff comes in. But photons go further in air than electrons. So they hit the cloth. So what you would assume from this, and I have these angles here are photon angles. The angle is greatest right in the middle. So you'd expect there to be a bright spot right there. Now we will look at the image itself. This is a whole, along a length. The first thing you notice, if you look for, is there's a bright line right up the middle. I believe that line is purely photonic radiation. So photons and electrons are both in this image, and they get sort of complicated. But the next, wrong one. You'd think I'd learn. Okay, here. Now the image down between the legs is right here. There's something strange about that image. It's a uniform width, has straight sides. The legs are curved. So how do you get a curved surface giving you straight sides on an image? Well, we'll have to now hit right. There we go, we got it. Here's the image cross-section again. This time, green means green, okay. The width of the air gap is from the top of one leg to the top of the other, so that's S. The air gap image is something smaller, which I call G. And then you have an area, a width, which is X. X is actually an image area. G is a non-image area. The interesting thing here is we have a right triangle. X is one side, R is a side, and then we have R up to the surface. And that's now the surface of the charge layer. And electrons will reach the cloth if the cloth is closer than D, which is the stopping distance of electrons. So the edge of the image gap starts when this distance here is R plus D. That formula called the Pythagorean theorem. X squared now is R plus D squared minus R squared. G, the width of the air gap image, is S minus 2X, which becomes 2 times the square root of 2 times D plus D squared. 2 times D times R plus D squared. So now we have G. That's the number we really wanted to know. To look at this, it gets simpler, I think, is if you just look at 1 centimeter D and a 2 centimeter D. See what happens. Okay, this is the formula for 1, this is the formula for 2. Now we can compile a table. What I've done is I've set up 5 points along the body, or along the leg, from the crotch to the ankle. S is the width of the air gap image. If we take the crotch, it's roughly, the leg at that point is roughly circular, so it's the circumference divided by 2 pi. We get this value. Same thing we do for the lower thigh and the ankle. The knee, however, is different. The knee has a kneecap that has a much different radius of curvature. But we need the top surface. So this is the radius of curvature of the kneecap. The calf has a different surface at the top and the bottom. We take the top surface. Now we got enough numbers to calculate G as when D equals 1. We get these numbers. At the ankle, we have a width of the air gap image of 6.1. If you measure it on the shroud, on a full-size image, that's too big. So then you go to 2, which is what I estimated earlier is the right value, and you get these, and you look at this, and now you're at 3.2. But when I got here, I discovered that 3.2 wasn't really correct when I measured it over there. It's actually 4. So it means that D, the actual true value, to probably 1%, or somewhere around there, is 1.7 centimeters. So that's probably the most accurate stopping distance for electrons you're going to get on this image. Okay, this is a diagram showing my rendition of the air gap. What you get is straight sides up to the lower thigh, and then it expands out. You get a bright line down the middle caused by photons. Okay, let's look at the head. The head is an interesting image. We look at it from the side. The thing that we see first is a jaw band running over the top of the head and under the chin. I don't show a beard here, but it's stuck underneath of the jaw band. Now, the person who's preparing this is looking at this, and he pulls the hair out, puts it over the jaw band to make the image look, the man's face, to look as neat as it can possibly look. So this is making him look lifelike. And also, they then put a strip of cloth around the neck, and this strip actually was tight against the neck, and you can tell that in the image later. So the airbag, this actually creates a bag over the head, and actually makes it fairly tight. I have the bag down above the head here. That's not true. It actually hits the top of the nose, hits here, and the hair actually extends up further. Now, what happens here is when this electricity gets there, you get all this charge. The electricity, the hair just goes crazy, and it expands. And so it pushes out as far as it can. It tightens up the surface, and the surface is pressed against the face as tight as the hair can do it. And that's a perfect surface for making this face image. This doesn't seem like something that just happened by chance. It's actually fairly interesting that everything is so precise. So now we go to the top of the head, and oops, 5. Okay, I'm going to talk faster. The jawband runs across the top of the head, and what you notice when you look at it is that the hair spans out the side, but it's anchored by the jawband. This gives us a deep air gap along both sides of the head. So when we go to the actual image, what do we see? Well, if we had the image that went high enough, we would see the jawband going across where this face image is. That's the image of the jawband. Along both sides, we have dark bands. This is caused by that deep air gap between the jawband and the hair. The hair is pushed out as far as it can go, and the cloth is lying over the hair and going around the edge. The cloth around the neck is right here, but this is not the neck cloth that we're seeing. We're seeing the shroud. It's pressed against the neck real tight. That shows you that that was tied tight. Here's the thing that's most interesting. It's the beard. There's a notch out of the middle. People have said the torturers pulled the middle of the beard out. I don't think so. The beard was underneath of the jawband. The person preparing the body looked at it and he said, oh, let's pull out this side. Let's pull out that side. But he left the middle. When you leave the middle, you get a square notch in the image. So that's where that square notch came from. So we're still at 5. That's good. Anyway, we have this image here of the hands, which the hands are different because they're away and they're small. There's less solution. There's less free electrons. There's a lot more leakage. There's low voltage. So the stopping distance of the electrons coming out of the hands is much less, and I put it at 1/2 centimeter. So when you form an image, you take your hands, if you laid it out here and put a cloth over it, the points where the cloth is touching the top of your fingers is where the image forms. It runs up the finger. When it gets to the top of the finger, it hits a knuckle. The knuckle's connected to a tendon. The ridge continues, and that happens on all the fingers. So the cloth actually has air under it, even when it goes to the back of the hand. So when you look at the image between the fingers, you get a dark band running up between the fingers. You get to the joints, and there's still air under the cloth. So the image continues dark. So what you get is what appears to be long, narrow fingers and a short hand. A lot of people say they're seeing bones. I don't think so, but I won't argue that. Okay, my conclusion is the body disappeared from our world and left an image on cloth created by electrons and photons. But I would like to end with one more statement. I believe that this is the only method that you're ever going to find to create this image. I thank you. If we have time, I can answer questions. Probably time's getting short.
So, I don't know. Drew is our timekeeper.
I can go as long as you can.
So, actually, we're going to have a Q&A session this evening. We are going to break for dinner. And then we are going to reconvene here at around 6:30. And so we're going to have dinner right over here. If you haven't bought a ticket, you can buy one back here. And it's join us for dinner. And also, once again, last call on my table back there if you want some Shroud stuff.
Later.
And so.